Welcome to videos on linear integrated circuits. So we are in the series of data converters. So this is the third part of digital to analog converters. So in the previous video we are discussing the integral nonlinear error and differential nonlinearity and integral nonlinearity. So we actually discussed for a 3-bit DAC. Uh, we have this straight line of slope 1, so which is indicating the ideal output of a DAC. For input of 0, 0, 0, this is the output, and the straight line indicates as the ideal output. This vertical lines over here indicate the actual output of a particular DAC, where we have certain deviation from this ideal line. So here this is slightly less than the expected output. Here it is slightly more than the expected output. Here it is almost 1 LSB down the desired output, and here it is half LSB more, and this is almost half LSB less. Now this is we can indicate by how much it is less or more by writing its INL, that is integral nonlinearity. So integral nonlinearity for a particular bit 0, 0, 0, here it is set as 0. Why means because we are getting the expected output as 0, and the actual output is also 0 here. So that's why there is no error. Even for 0, 0, 1 bit, the expected value is 1 by 8. We are getting the output also as 1 by 8. There is no error. For 0, 1, 0, so for 0, so for 0, 1, 0, we expected the output to be in this level, but we are getting an output which is over here, which is less than the expected value. That by how much it is less will be always expressed in terms of how many LSBs it is down. We know that 1 by 8 is 1 LSB, that is here 2 units happens to be 1 LSB. Since it is less by only 1 unit, it is half LSB. Since it is less than that, we write it as minus half LSB. And for 0, 1, 1, this is the expected output voltage, and we are getting actually more than the expected one, so more by half LSB. Now that's why it is plus half LSB. And we can see for 1, 0, 0, the output is over here, the expected value is 4 by 8, actual value is 3 by 8, so it's actually less by 1 LSB, so that's why it is minus 1. So likewise we can find what is the INL. INL is for a particular bit, what is the expected value and what is the actual value, how much is the deviation from the actual value, how much is the deviation from the desired value is the INL. So as you can see here, so here it is as per the expectation, there is no INL. So INL is 0 here, INL is minus half LSB, INL is plus half LSB. Now again INL is minus 1 LSB. This is minus, it is plus half LSB. Here it is minus half LSB. Now it is 0. So that's what is listed over here. And the DNL corresponds to, once we have this output, actual output as 0, our next output for 0, 0, 1 should be 1 LSB up. So we are looking at, with respect to this, what's my next output is. If the next output is exactly 1 LSB up, we'll write there is no differential nonlinear error. As you can see here, for 0, 0, 1 we had 1 by 8 as the output. We expected for 0, 1, 0 the output would have been here. Now actually the output is bit less. By how much it is less? So we expected the output to be here compared to this, because compared to this and this, it's a 1 bit more. It is 0, 0, 1. This is 0, 1, 0. We expected the output to be over here, but it is half LSB down. So that's why we write the DNL of 0, 1, 0 is minus half. Just see here, this is the present output. Assume that this is present output. We expected for the next bit, so 0, 1, 0, next bit is 0, 1, 1. We expected the output to come out here. So this is for this present value. If the input is increased by 1 LSB, that is, if the input changes from 0, 1, 0 to 0, 1, 1, from 0, 1, 0 to 0, 1, 1, the output which was over here is expected to go up by 1 LSB. But actually you can see from this value it is going here. Its expected value here corresponding to this it is 1 LSB up, but it is more than that by one more LSB. So that's why we say the DNL at 011, the DNL at 011 is 1 LSB, because it was expected to be here. Now we are not looking at the ideal value of the expectation compared to the previous value, because the bit is increased by 1 bit. When the bit is increased by 1 bit, the output was supposed to go by 1 LSB. Since it is going up by more than 1 LSB, we are looking at by how much it is going above from the desired value. The desired value was this. Now we are getting the desired value, the actual output is this. It's actually 1 LSB up. Now for the next bit it is 100. From this it was supposed to go over here. So it was supposed to be, this is the actual output expected, but we are getting it here. Now compared to this value is 1.5 times down. So 1.5 LSB down. So that's why we write for 100, the DNL is minus 3 by 2. So why it is minus 3 by 2 is, this is the actual value. For the next bit, this would have been 1 LSB up, which would have been here. But actually output is over here, which is actually from this point 1.5 LSB down. So that's why it is minus 3 by 4. Now from this, if the bit is increased by 1 bit, that is from 100 to 101, the expected output was here corresponding to this, it would have been here, but the actual output is far above that. So this is the expected one, we are getting it over here. We expected here, we are getting it here. By how much it is above? It is above by 3 by 4 3 by 2 LSB, that is 1.5 LSB. So that's why for 101, the DNL is 3 by 2. Now from this 010, when it is 110, the expected value was supposed to be here. The expected value is here, but we are getting the actual value is here. Now it is from here, by how much it is down? It is 1 LSB. So that's why it is minus 1. And for the final 111, for this as the present value, for next bit increment, the output would have been over here, but the actual output is half LSB up. That's why it is half LSB. So likewise, while finding the DNL, we actually look for the previous value, and the next value should be 1 LSB up. We are looking at whether it is above and below that 1 LSB. If it is equal to 1 LSB up, we write the DNL as 0, because it was supposed to be 1 LSB up, it is there. If it is more or less than that 1 LSB, then we write the DNL. So that's why we didn't had any DNL for the 000 and 001, because they were exactly 1 LSB up from the previous value. But here for 010, it is not 1 LSB up, it is actually half LSB down. So that's why we write as minus half. So all these values, which is minus 1, 1, 1 by 2, 3 by 2, these are all in terms of LSBs. Okay, this is what we are trying to look at. The same explanation, this is an important discussion we are supposed to look into. The maxima of INLK and DNLK are being given over here. The INL value maximum is 1 LSB, and the DNL value is 1.5 LSB. Of course, we'll just discuss about this non-monotonicity and monotonicity in the coming slides. So we shall just see one important relationship between INL and DNL. If you know the DNL values, we can certainly estimate what is the INL. So this INLK is given by summation of DNL from DNLi, where I is ranging from 0 to k. Assume that you are supposed to find the INL for this 011. If you want to find the INL for 011, so you have to sum up all the DNLs of this. So this plus this is 0, 0 plus minus half is minus half plus 1 is half. So the entire addition of these DNLs from 0, 1, 2, 3 happens to be the INL of this particular bit. Likewise, if you want to find the INL of 111, you add all the INLs starting from 0 to 7. It is 0 plus 0 nothing, this is minus half, so this will become plus half. Next it is minus 1, next it is plus 0.5, next it is minus 0.5, then it is 0. Minus 0.5 plus half is 0. So that's how we get the INL as 0. We shall take up two more examples to get hold on this INL and DNL. So before that, we shall see this what is monotonous and non-monotonous DAC output. Uh, we know that monotonous output, ideally for every 1 bit increase in the input, the output increases by 1 LSB. So that is, if your input increases by 1 LSB from, assume that it is 000 to 001, so there is an increment of 1 LSB at the input, the output should also increase by 1 LSB. So that 1 LSB is given by FSR divided by 2 power n. That is, output voltage is monotonously increasing with the input. So we know that for every change in the input voltage which is increasing, the output voltage should monotonously increase. If input increases, output should also increase. However, sometimes for 1 bit increase in the input, output may increase by only half LSB or may not increase at all. So we have seen in the previous examples that here you can see from this to this, the output input has increased by 1 LSB, output also has increased by 1 LSB. But you can see here from this 001 to 010, input has increased by 1 LSB, but the output has not increased by 1 LSB. It was supposed to be here, but it is over here. Now here it is half LSB increment. If you come to this from 010, it is going to 110, which is 1 LSB increment. But if you see the output is constant. So there is no increment at all. That's what we are trying to observe here. However, sometimes for 1 bit increase in the input, the output may increase by only half LSB or may not increase at all. Still the output is called monotonous. Why we say it as monotonous is at least we have to be happy that output is not decreasing. So as long as the output stays and output increases, we say the output as monotonous. But in some rare cases, for 1 bit increase in the input, output may decrease by half LSB. I can say we are looking at the output is actually decreasing by half LSB. That is, the present output is less than the previous output. Assume that you have increased the value of input by 1 bit. Actually, you had some output. That output has actually reduced upon increasing the input. So this is not acceptable. That is, present output voltage is minus 1.5 LSB less compared to the previous output. If the output is less than minus 1.5 LSB compared to the previous output, we call it as non-monotonous output. Now, why it is called as non-monotonous is because you are supposed to get a increased output voltage for every increment in the input, but here we are getting a reduction in the output voltage. If the reduction is more than 1.5 LSB, that is, if it is more than minus 1.5 LSB compared to the previous value, we call such outputs as non-monotonous output. Now it should be less than even if it is minus 1.5 LSB, it is still taken as monotonous. If it is less than minus 1.5 LSB, we call it as non-monotonous output. So in the previous case, we had it as minus 3 by 2. Still it is not, still we can call it as monotonous because it is not going below minus 1.5. Whereas while increasing, the increment can be anything more than, it can be 0, it can be half LSB, it can be 1.5 LSB, it can be 2 LSB also. But it will be still called as a monotonous. But if the output decreases by more than 2 LSB or 1.5 LSB, we call it as non-monotonous output. We shall just have a look at these two examples. One more example here, you can see this is 0, we are getting it. So this is the straight line indicate the ideal value. These are the practical values. We can actually find out what is INL and DNL. So in the next video, we shall discuss this particular graph and try to identify what is the INL and DNL for this example. So maybe after studying these two examples, the INL and DNL will be more clear.